Can everyone see my slides?
Yes, thanks.
Okay, great. Yeah, so I'm really excited to present our work, which is called Learning Latent Representations to Influence Multi-Agent Interaction. And this was work done in collaboration with Dylan, Ryan, Chelsea, and Dorsa. So we're in this work, we're interested in studying multi-agent interactions between robots and other non-stationary agents like humans. Oh, also feel free to interrupt at any point with questions that might arise. So before I talk about robots, I wanted to first talk about people. And specifically, let's first think about how people interact with each other, such as in this hockey example. So the player on the left here is currently aiming from the right side of the goal. But the next time he approaches the goal again, he might pick a different strategy. For example, he might aim from the left side instead. And of course, this makes the goalie's job really difficult because this means that he has to deal with the different strategies of the opposing team during each offensive play. And so similarly, when robots interact with humans or other robots, these other agents are non-stationary. And what I mean by this is that they update their behavior in response to the robot. And so prior work for handling these multi-agent interactions would explicitly model the low-level policy or other low-level attributes of the other agent. But people can very naturally interact with each other with little to no effort. For example, people can compete in a game of chess or work together to carry something heavy or navigate through lanes of traffic. And we think that they can do this by keeping a high level representation of the other person as opposed to tracking the low level policy. And so we recognize that a lot like in human-human interaction, robots can also capture these other agents that they're interacting with these high-level representations that can change over time. And we refer to these representations as their latent strategy. So for example, consider these two robots playing air hockey against each other. The ego agent on the left is a reinforcement learning robot that's tasked with blocking the incoming shots, while the other agent on the right is a rule-based robot that can dynamically change its strategy depending on what the ego agent does. So the ego agent only observes the Y position of the puck as well as its own position. And to construct a non-stationary problem setting, the X position of the puck isn't given to the ego agent. Instead, it has to be inferred from its earlier interactions or essentially the transitions or rewards that the ego agent receives. And the ego agent can move its paddle up and down the x-axis like that. And on the other side, the other agent has different strategies which correspond to aiming in different directions, specifically to the left, down the middle, or to the right. And so we define an interaction to be the sequence of states, actions, and rewards that the ego agent receives. Then after each trial, the other agent will select a new strategy based on the previous interaction. And we call this the latent dynamics of the other agent's strategy. And as you can see on the bottom left here, we assume that the strategy of the other agent is some unknown function of its previous strategy and the previous interaction with the ego agent. And so the most important part is that the ego agent never observes the strategies or the actions of the ego agent, or sorry, of the other agent. And so because naive reinforcement learning algorithms assume that the environment is stationary, they don't actually model the changing opponent. And when a reinforcement learning agent is faced with a non-stationary agent, such as the one on the right here, the RL agent will learn to just pick one mode to block. And here it's blocking on its left side. So to summarize our setting, the EO agent is interacting with another agent, which induces a potentially different NDP in each interaction. But we assume that the other agent is following some dynamics. But what that dynamics is unknown. And so for the robot to be able to adapt to the other agent, it first needs to model how the other agent's behavior is changing. Like I mentioned earlier, prior work often focused on estimating the policy of the other agent and how it changes. Instead, our approach will try to learn a high-level representation of the other agent that can change over time. And so to learn this representation from data, we first train an encoder that takes in the previous interaction, tau k minus 1, and it will predict the next interaction's latent strategy, zk. Then from this representation, the decoder will reconstruct the rewards and the transitions of the next interaction. And the whole point of this latent representation, Z, is to capture what the other agent will do next. And so we train this encoder decoder model to maximize the log likelihood of the rewards and the transitions that we're seeing across all of the interactions. And so having learned a model of the other agent, we can now train a policy that's conditioned on the predicted latent strategy. And this policy, because it's conditioned on the latent strategy prediction, will give us different behaviors for different predictions. And it basically gives the ego agent the ability to react to the other agent. So to recap, during training, our approach first trains an encoder-decoder model that learns the representation of the other agent. Then we train a policy conditioned on this representation, so the agent can react to the other agent depending on what it thinks the other agent will do next. Then putting all of this together during a new interaction, the encoder will predict the other agent's latent strategy. Then the ego agent will carry out the policy conditioned on this prediction, and this whole process repeats. So we call this whole framework learning and influencing latent intent, or LILI. And our first experiment is a simple navigation task where the ego agent, which is represented by the teal circle, is trying to capture the other agent, which is represented by the gray circle. So the ego agent always starts each interaction at the same spot, T1, while the other agent sits somewhere along the shaded blue circle. And during each interaction, the ego agent needs to capture the other agent as quickly as possible. But it never observes the position of the other agent, and instead it will receive reward based on how far they are from each other. So the other agent is only allowed to move between interactions. And specifically, it will move either clockwise or counterclockwise, depending on whether the ego agent's final position is inside or outside of the circle. And so here we visualize the trajectories that are taken by the ego agent in teal, where the teal circle, the filled in teal circle represents the final position of the agent, and each frame corresponds to a single interaction. So this first policy is trained with soft actor critic, which is a standard reinforcement learning algorithm that doesn't model the other agent. And this policy, as you can see, at convergence moves to the center of the circle in each interaction. And that's because without any knowledge of or any mechanism to actually infer where the other agent is, the center of the circle is where essentially receives the highest reward. So in contrast to this, our method, Lily, can successfully model the other agent's behavior, and during each interaction, successfully captures the other agent. But notice that the other agent is captured along this lower part of the circle, which is highlighted in red. If the goal is to reach the other agent as quickly as possible, then ideally what the ego agent should do is have the other agent be positioned at the top of the circle where the ego agent is closest. So in other words, the ego agent should influence the other agent to move towards the blue region. So let's go back to our original objective. So earlier we said that the ego agent is optimizing this objective, this RL objective, to react to the other agent. Instead of simply reacting, what we actually want is to learn a policy that can influence the other agent's strategy. And we recognize that this influential behavior can be learned by maximizing the long-term rewards across interactions. And so what we do here is we sum the rewards across multiple interactions, and this objective will essentially motivate the ego agent to take actions that leads to more desirable long-term future strategies in the other agent. And so now returning to our navigation example, as we expected, we see that the Lily agent with influence learns to trap the other agent at the top of the circle. And this is where the target is closest to the ego agent, and therefore where it receives the highest rewards. So here's another visualization of the same thing. Here we're plotting the rewards collected during each interaction. And we see that Lily with influence almost matches Oracle performance, where the Oracle is given the ground truth position of the other agent, while Lily without influence earns slightly lower rewards. And so here we're looking at another task that's simulated in CARLA. And during each interaction, the ego agent is controlling the blue car, and it needs to pass the other agent, which is controlling the tan car. So the other agent acts in such a way such that it will always move to the lane that the ego agent occupied in the last interaction. And the ego agent receives -1 reward for any collisions or lane violations, and 0 reward otherwise. So the converged soft actor critic agent, as you can see, will change to the left lane in every interaction, even when the other agent moves to the left lane as well. And this leads to collisions with the other agent. On the other agent will switch to, and it switches to the opposite lane accordingly. And so here, because the strategies in the setting are equally rewarding to the ego agent, Lily without influence results in the same performance as Lily with influence. And so we next tested our approach in the air hockey game that was described earlier. So as a reminder, the other agent will strike the puck either to the left, down the middle, or to the right. And after each trial, the other agent selects a new strategy based on the most recent interaction. And more specifically, what the other agent does is it always aims away from where the ego agent last blocked. So the ego agent earns +1 reward for successfully blocking the puck. And now let's pretend the robot, for some reason, has an easier time blocking on its left side, and we give it +2 reward for blocking shots that come down the left. And so what this means is that influencing the opponent to aim to the left side more often will lead to higher long-term rewards. So we first trained a policy with soft actor critic. And again, it doesn't model the opponent. And so this agent learns to only block one mode, which is its right side. But near the end of training, we can see that it switches to blocking to the left side instead every time, which earns it higher reward. So in this plot, instead of rewards, we're plotting the success rate over training. And we see that the final policy achieves about a 40% success rate. While a random policy, which just takes random actions at every time step, has a success rate of around 20%. And this is just to highlight the difficulty of the task. And so we see that Lily can block a lot more successfully than soft actor critic. But because it doesn't, because it's not explicitly trained to influence the other agent strategy, it won't get that bonus reward for blocking left every time. Here we plot the success rate, and Lily blocks a lot more successfully. It blocks about 80 to 90% of the time. And finally, we compare it to Lily with influence. And so this agent can, as you can see, it's manipulating the other agent to alternate between left and middle shots. Let me replay that. Between left and middle shots. And by doing this, it's actually achieving higher overall rewards. So looking at the success rate only, Lily with influence has a similar success rate to Lily without influence. But where we actually see a difference is when we look at how frequently the opponent is firing left to the middle or to the right. And Lily with influence leads its opponent to fire left the most often, as you can see here. It's firing left 41% of the time, while without influence, the distribution over the strategies is roughly uniform. And it's important to note that since the other agent, the rule-based agent, is designed to always change the direction of its shots, the maximum ratio or the maximum percentage of left shots is actually 50%. And so finally, we tested the policies that were learned by soft actor critic and Lily against a human expert. So here we just have the human expert follow the same set of strategies as the robot opponent from the earlier setting. But the key difference here is that the human has imperfect aim. So it's introducing noise that wasn't seen during training. So the soft actor critic agent success rate is about 45%, while Lily's is about 73%. And this is, as you can see, a drop from the earlier 80 to 90% success rate. And we hypothesize that this is due to the noise that the ego agent wasn't trained with. And so far the other agent strategies have been pretty straightforward. And we wanted to better understand the robustness of Lily, specifically to more complex agent strategies. And so here in this first setting, we introduced noise to the other agent strategy in the point mass navigation task. And so originally the other agent took fixed size steps between interactions around the circle. Uh, that's illustrated here in gray. So instead, we added different levels of noise to the other agent step size. And essentially, this table is showing what the final rewards achieved by the Lily agent was against against other agents with varying levels of noise. And so we find that the performance of Lily is degrading as the magnitude of noise increases, but it still mostly successfully models the other agent strategies and outperforms the baseline soft actor critic. And we next wanted to understand whether Lily could model strategies that depend on multiple previous interactions. And so once again, we're looking at the point mass navigation task, but earlier we had assumed that the other agent strategy only depended on the immediate last interaction. And here we're defining the other agent such that it moves based on the last n interactions. And so we expect Lily to perform worse as n increases because this essentially means the opponent's strategies become more complex and harder to model. It's also important to note that we generally, when interacting with agents like humans, we generally expect n to be quite small. But nonetheless, we see that the performance of Lily does degrade a lot more compared to adding noise to the other agent strategies. And so here we're looking at the performance of the Lily agent against agents with, so these numbers correspond to n as in how many interactions the other agent strategies will depend on. So the other agent strategies depend on the last n interactions, and we have different values of n here. And so generally our results show that Lily is capable of modeling non-Markovian strategies as long as it depends on, I guess, reasonably long interactions histories. So this is, in terms of future directions, we would like to study how Lily interacts with other agents with increasing complexity of strategies. And in terms of complexity, there are different axes, but we wanted to illustrate a few settings where essentially we have air hockey on the side of less complex, while for example, in situations where we have reinforcement learning agents as the other agent, we consider those to be increasingly complex. So to conclude, we can often capture the behavior of non-stationary agents through these high-level representations. And with these representations, the agent can learn to anticipate and even influence the other agents across repeated interaction. So as I alluded to earlier, some future directions that we're interested in are increasing the complexity of the other agent strategies, as well as looking at human in the loop learning. So earlier in the setting where we tested the learned policies against the human expert, we did have the human expert try to reflect the strategies that were followed by the robot opponent that the ego agent had trained with. But to fully capture human behavior, we would expect to have to essentially train alongside humans. And of course, this brings about additional challenges due to I guess, the lack of sample efficiency in reinforcement learning algorithms. And finally, we looked at two agent systems in our experimental settings, and extending to more agents, systems with more agents is also would also be an interesting future direction. And there are some challenges associated there due to the fact that there are interactions where the ego agent so essentially what I mean here is the ego agent, we want the ego agent to interact with n other agents, where those other agents might potentially be interacting with each other and therefore affecting what those agents are doing. And those increased, or so essentially those agent-agent interactions introduces additional challenges for the ego agent in terms of modeling. So I'm happy to take any questions now.